Good morning, everyone. In today's lecture, we will learn about the soil physical properties. What basically soil is? We all know that soil is a polyphasic system comprised of mineral, organic matter and fluids, and it is also a living system. And the soil properties are specific features which the soil possesses by the virtue of interaction between the different soil forming factors and processes. And the soil functions as a sum total of its properties. So as we know that for description of any substance, we need to know about the different properties which we use to describe that substance. For soil, we have generally the three set of properties: physical properties, chemical properties, and the biological properties, which interact with each other to represent or make the soil function in a way in which we see it in the present form. And talking about the soil physical properties, which we will be talking about today, we have the aggregation and soil structures such as sealing, compaction, porosity, water movement and availability, which are some of the physical properties. By physical properties, we mean the properties which are guided by the physical forces. Now, the very important soil physical properties which we will talk about today are the soil color, soil texture, soil structure, density, soil porosity, soil water, and soil aeration. Now, to begin with soil color, as most of us know that whenever we visually see any object, the most obvious thing which comes to our mind is the color, and the same with the soil. So whenever we go to a field, the most obvious thing which we notice about the soil is its color. And if you see from ancient time, the way in which the soils have been classified, it was primarily based on soil color, where we classified soil as black soil, red soil, yellow soil, brown soil, or gray soil, depending on the color which it represents. And it is a useful tool for providing information about soil without doing any chemical analysis. And what are the factors on which soil color depends? Mostly the soil color depends on soil mineralogy, the soil organic matter content, soil moisture, soil texture, and the oxidation reduction state of the soil. So in terms of mineralogy, if we are having a dominance of iron, the soil will have a more reddish color. Soil organic matter content, as we can see in this picture, high organic matter content soil have a darker shade compared to soils with low organic matter content. Similarly, with the increase in the soil moisture content, there is a darker color which we observe in the field compared to a low soil moisture content. Soil texture, heavier the texture or more decay content, more darker the soil color tends to be. Also, the oxidation reduction state or the state of oxidation reduction in the soil decides the soil color. And generally under waterlogged condition or under reduced condition, the grayish or greenish tinge in the soil is. For measuring the soil color, we have the Munsell color chart, which is used for measurement of the soil color, and the soil color is described with aspects to three parameters: hue, which refers to the dominant spectral color, the value, which is with the relative darkness or lightness of the color, and chroma refers to the purity of the color. Generally, color notations are done as 10YR 5/3, where 10YR is the hue of the color, which is yellow-red. 10YR, Y stands for yellow, R stands for red, while 5 is the value and 3 is the chroma of the color. And under reduced condition, generally most of the soil you will see that it varies from a color of brown to black to red, with whitish tinge coming with the increase in the salt content or when there is a lack of organic matter content. And under the reduced condition, we have dark grayish, greenish, or pale olive or dark bluish gray tinge, which are observed under the reduced condition or under waterlogged condition. So soil color is an important soil property, and it is one of the most obvious soil properties which we observe in the field. And with the differences in the soil color, we can get an idea about the different management practices or the aspects with respect to the soil property changes in soil properties. Like darker color soil will definitely mean that it has got a higher organic matter content most of the time, or generally it will have a higher water holding capacity or more clay content. But definitely it needs ground truthing or ground verification, or the analysis which we are doing physically needs to be confirmed with the laboratory analysis as well. The next important soil physical property which we will be discussing is the soil texture. Texture, as we know, that it is the relative proportion of the different particle size fractions, visually sand, silt and clay. And the sand, silt and clay are directly derived from the parent material by the 5 factors of soil formation. And if you see the size range generally for sand, it is 2 to 0.2, for fine soil 0.2 to 0.02, and then silt varies from 0.02 to 0.002 mm, whereas clay fraction is less than 0.002 mm. And the International Union of Soil Science and the USDA system, they have certain difference in the classification range, though it is obvious that 2 to 0.002 or less than 0.002 are the fractions which are considered in the soil particle fraction or for the purpose of defining soil texture. And generally the texture is expressed as a percent of these particles, 3 fractions, in 100 gram of soil. And sand and silt, they are the coarser fragments which are referred to as the skeleton, and clay is referred to as the flesh of the soil, or clay is the matrix where the different reactions takes place, whereas sand and silt together gives the structural support or the skeletal support to the soil system. And this is the textural triangle which is used for determining the soil texture once we have the soil texture percentage of the 3 different categories of soil separates after the laboratory analysis. And as per the International Union of Soil Science, there are 12 textural classes which are dominantly found in the soil system. And after getting the different silt, clay and sand fractions, we draw lines parallel to each of the triangle, and the point of intersection gives the texture of the soil. In the laboratory, the soil texture is determined with the help of the Boyka's hydrometer method or the international pipette method, whereas in the field it is determined with the help of field method by using water and trying to make a dough or a ribbon and getting the feel of the texture between the fingers. And the ribbon length, depending on the ribbon length, we can classify the soil texture. When the ribbon length for sandy soils, no ribbon formation takes place. If the ribbon formation is less than 2.5 cm, it is in the loam range. If the ribbon length formed in the field is 2.5 to 5 cm, the soil is generally in the clay loam texture. And depending on the ribbon length, if it is more than 5 cm, it is in the clay texture. And generally, if we see the feel of the 3 different soil separates, the sand gives a very gritty feeling. The silt fraction gives a feeling which is intermediate between gritty and smooth, or we can say it gives almost the feel of talcum or a smooth slippery feeling, whereas for the clay fraction it gives a sticky and smooth feeling. So this is how the soil texture is determined in the field with the help of field method, whereas in the laboratory it is determined with the help of hydrometer or international pipette method. The next important soil property, which is important physical property, is the soil structure. So texture refers to the 3 size fractions, that is sand, silt and clay, whereas soil structure is the arrangement of these primary and secondary soil particles. And the structural units are called PEDs and have distinct boundaries and well-defined planes of weakness between the aggregates. And these particles, that is the primary and secondary particles, they are bound together by different cementing agents to form the aggregates or the PEDs. And these cementing agents, mostly they may be organic matter or clay even, and oxides of iron, aluminium, calcium carbonate, and the microbial activity also plays an important part in binding of the soil aggregates. And The soil structure is classified into 4 types based on the shape and arrangement of the particles. It is like plate-like, columnar, block-like, spheroidal or granular, and the structure, it can either be single grain or massive as well. And for agricultural purposes, generally the spheroidal or granular structure is taken as the best. And if you see the structural classification, this refers to the granular structure, and the nomenclature of the structure is mostly based on the shape or the shape of the particle. Like the block-like is almost having the similar dimensions in as both lengthwise and as width. Prismatic structure or columnar structure they are more elongated compared to the width. Platy structure, they have a width is more and the length is less. And of all these structures, the granular structure is best for agriculture purposes, where the porosity and the infiltration rate and the soil aggregation is best maintained. And grade of the soil structure, depending on the strength and durability of the aggregates, they are classified as weak, moderate and strong. And the structural classes may be defined as very fine, fine, medium, coarse or very coarse, depending on the diameter of the aggregates, which we generally do in studies when we are considering the soil profile study. Now, what are the factors influencing the soil structure formation? One is the flocculation and the aggregation process. So, more the flocculation and aggregation process, more will be the stability of the structure. Vegetation, plant roots and microorganisms have a definite role in determining and forming the soil structure, where all these three have a positive correlation with the formation of the soil structure and the aggregate. Cations present in the soil, particularly with the presence of divalent cations like calcium and magnesium or hydrogen ions, these help in the soil aggregation and formation of better soil structure, whereas monovalent cations, particularly sodium, it disperses the soil and does not allow the soil to form a good structural aggregate or stable aggregates. Soil organic matter, again, it is positively correlated with the structural stability, and more organic matter leads to better soil aggregate formation. Clay particles and clay organic matter interaction. So, soil, based on its texture, clay soils will have better aggregation compared to sandy soils, or the proportion of clay as it increases, the tendency of the soil to form aggregates increases. Soil management practices like tillage and amendments, particularly with respect to tillage, it has got a negative impact on soil structure, because more tillage or more disturbance in the soil system results in breaking of the soil structure and soil aggregates, whereas amendments generally have a positive impact on aggregation. Like if we take the case of sodic soils, addition of gypsum result in the formation of better aggregation. And the soil aggregates generally are classified into 2 categories: the macro aggregates, which are more than 0.25 mm, and the micro aggregates, which are less than 0.25 mm. And the macro and micro aggregates generally modify the soil properties in different ways. The micro aggregates results in like better protection of the soil carbon, whereas the macro aggregates increases the infiltration rate. And the microorganisms, particularly talking about the mycorrhiza, they have an important role in formation of the macro and micro aggregates, and formation of the stable aggregate is an important prerequisite for sustainable soil management. Whenever we are talking of soil conservation or soil erosion, the aggregation process is positively correlated with the negating the effect of erosion, because the splash, which is the starting point of any erosion, where there is dispersion of the soil particles, better your aggregation, better will be the tendency of the soil to prevent itself from process of dispersion. Now, the next important soil property or the soil physical property is the specific surface area. This is defined as the amount of surface area present per unit weight or volume of the soil, and it is expressed as centimeter square per gram or centimeter cube. So the specific surface area is an important soil property as it has influential role in water retention, swelling, plasticity, cation exchange capacity, and nutrient availability of a particular soil. And if we see the three different size fractions like sand, silt, and clay, the clay generally has the highest specific surface area followed by silt and sand, and that also makes clay the most reactive fraction in the soil system. The next important soil physical property is the density. Now, talking of density, generally we consider two types of density in the soil system, that is the bulk density and the particle density. Particle density, it refers to the density of the soil solids only, which is given by the formula of mass of soil solids by volume of soil solids, whereas bulk density includes the bulk of soil including soil solids and the pore spaces. And for most of the practical purposes, we take particle density as constant to be 2.65 megagram per meter cube, whereas the bulk density is variable and it is a very dynamic property of the soil which changes with the impact of the different management practices. And the porous textured soil generally have a higher bulk density compared to the fine textured soil, and mostly all the management practices which has a greater role in sustainable agriculture, they will tend to reduce the bulk density of the soil, because lower the bulk density, better will be the porosity, and better porosity indicates higher infiltration rate, better root growth, better aeration, whereas heavier bulk density or higher bulk density indicates a more compact soil which interferes with the infiltration purpose, with the root growth, with the germination process of the plant. So our tendency would be to optimize the bulk density of the soil, and this can be done through reduction in the tillage operations or increased organic matter content. Generally, the bulk density is measured with the help of the core sampler, where the volume of the core is essentially taken as the volume of the soil, and the mass of the soil is determined after oven drying, and the mass by volume gives the bulk density soil. And if we see the bulk density and root growth relationship based on soil texture, so as we move from sandy soils to the clay soils, the bulk density reduces, ideal bulk density reduces, and also the marginal bulk density and the root restricting bulk density also changes depending on the soil texture. The next important soil property is porosity, which is a derived property depending on how the soil particles are arranged, because we know that the soil is composed of three phases, that is solid, liquid, and gas. And when the soil particles or the organic and mineral matter is arranged, they are arranged in such a way that in between there are pore spaces, which results in the movement of air and water through the soil profile. And it is the ratio of the volume of pore space to the total volume of the soil which is defined as the porosity. The macro pores, they are generally 0.06 mm in diameter or more, and the micro pores are less than 0.06 mm in diameter. And the formula of porosity is given by 1 minus bulk density by particle density into 100, which is expressed as percentage. So moderate porosity like optimal soil has 50% of solid space and 50% pore space, and any deviation from this ideal condition results in soil compaction, or there will be very high infiltration rate or very high aeration, and a balance between the solid and the pore space is required to have optimal plant growth and productivity, and from all aspects for maintaining a sustainable crop production. The next two important soil physical property which we will discuss are the soil water and soil air. So soil water and soil air, they are the two phases which are residing within the soil pore spaces. And infiltration, these are some terminologies related to the soil water and the movement of soil water within the soil profile. So infiltration, it is the entry of water at the soil air interface, where infiltration is a very important phenomena from soil conservation point of view, as it decides the amount of water entering into the soil profile and amount lost as runoff, and it is dependent on soil texture and structure. The hydraulic conductivity, it is the velocity of the water within the soil profile in response to a particular hydraulic gradient, whereas permeability, it is the intrinsic property of the material and it has nothing to do with the fluid characteristics. Now, when we talk of soil water, generally the plant available water is more of a concern for us, which refers to the water which is available to the plant within a particular pressure range. And there are 3 specific points at which measurements are taken. Field capacity, that is at the water present in the soil at -1/3 bar. The permanent wilting point refers to the water which is present at -15 bar, and the hygroscopic coefficient, that is the water mostly in the vapor form, at -31 bar. And the soil water between the field capacity and the permanent wilting point is generally referred to as the plant available water, whereas the water beyond the wilting point is the unavailable water. And the 2 most important soil property which determines how much soil water is retained within the profile is referred to is the texture and the soil structure. And in this table we can see that depending on the variation in soil texture, the available water content per meter soil changes. And for sandy soil it is between 25 to 100 mm, whereas for loamy soil 100 to 175 mm, and for the clay soil it is 175 to 250 mm. So the amount of water which is held within the soil profile, it is highly guided by the texture and soil structure. And clay content generally has a positive impact on the water holding capacity, and the higher clay content will also lead to more micropore spaces and improved soil structure and aggregation. More the micropore, more will be the capillary retention of the water. So we see that as we move gradually from sandy to clay soil, the quantity of water which is held within the soil profile within a meter depth increases. But if we see that the force with which the soil holds the water, it is also dependent on the texture and the structure. So more the clay content, they will hold the soil water with more affinity compared to the sandy soil. And physically viewing how the quantity of soil water looks at permanent wilting point or field capacity or at saturation, like these gravitational water. So initially when irrigation happens or when there is high rainfall, the soil is saturated with water, and then there is a movement of water downward under the force of gravity, and this water drains out very quickly, which is referred to as the gravitational water. At field capacity, the water is held with the forces of capillary, and between field capacity and permanent wilting point, the water is held with the force of capillary and it becomes slowly available to the plant. And after the wilting point, beyond the wilting point, the water is held, though there may be some quantity of water, but it is held so tightly that the water becomes unavailable to the plant. So if our water is available within this range, our plants can grow comfortably, but as the water content reduces or as the water becomes held by the soil profile with more and more force, the roots face more difficulty to extract the water from the soil profile, and thus it indicates that we have to irrigate or we have to provide supplement water to support the plant growth. And this is again a representation of the air water within the soil profile at gravitational, at field capacity and at the wilting. The next important soil property is soil air or the soil aeration. And if we see the atmosphere and the soil composition, with respect to nitrogen and oxygen it is almost safe, but with respect to carbon dioxide, the soil air is more enriched compared to atmosphere. And this is mostly because the microbes and the plant roots, they are always respiring within the soil system, and the exchange of gases between the atmosphere and the soil occurs at a rate which is less than the amount of CO2 produced. So the concentration of CO2 is higher within the soil system. Now, this air is essential for the growth and respiration of the plant roots and microorganisms. And if the soil becomes saturated with water for a prolonged period of time, the availability of oxygen gets zero, or the availability of oxygen is reduced, and it becomes a reduced condition within the soil system, which hampers the root growth as well as the growth of the microbes. The waterlogged soil has a different chemistry compared to a well aerated soil, so a balance between the soil air and soil water content is highly essential to ensure a proper crop growth. The composition of soil air is different from atmospheric air already, as we have discussed. The exchange of air occurs at the soil air interface by the process of diffusion, and the water content, porosity, density, soil structure and texture all affects the soil aeration process. So this was in a nutshell what we call the soil physical properties. And one thing I want to tell is that no soil property reflects itself exclusively, because all the soil properties are in turn interfering with each other, or they are interacting with each other, and what we find is a cumulative expression of the different soil properties. So that is all about the soil physical properties. Thank you.